Hello there, and welcome to Mr. Sleepy Science, where curiosity gently arrives at the edge of night, and science spreads itself out slowly, carefully, until the unknown feels a bit nearer. Tonight, we're traveling somewhere that almost nobody ever has. Not because we lack the desire, but because the earth itself appears to fight against us. We're heading to the top of the world, beyond the snow and the stillness, past the freezing winds and the shining ice, to a spot that has been locked away for longer than humans have walked the planet. Under the North Pole's glaciers, there is a secret world, dark, enormous, strange, and nearly impossible to reach. And for all our technology, all our dreams, and all our restless need to discover, we still cannot truly access it. But before we go beneath the surface, I'd love to know, where are you listening from tonight? And what's the temperature where you are? Maybe it's warm, maybe it's chilly, but I can promise you it's nowhere near as freezing as the place we're about to explore. If this journey feels like the kind of calm curiosity you appreciate, I'd be deeply thankful if you'd like this video or subscribe to Mr. Sleepy Science. It helps this peaceful little corner of science reach more people who might need a quiet moment too. Now, get yourself comfortable, calm your thoughts, and follow me northward, because the story we're sharing tonight has been trapped beneath the ice for millions of years. The top of our planet is an unusual kind of frontier. It's not a mountain to scale or an ocean to cross. It's a place that doesn't really stand before us as much as it hangs over us, buried under hundreds, sometimes thousands of meters of ice. When we picture the North Pole, we usually imagine an endless blanket of white reaching to the horizon, a flat plain broken only by the occasional bear or expedition flag. But that's just the surface. Under that frozen desert is a landscape we hardly know. Rivers that move without ever meeting the air. Lakes locked away from the sun for longer than our species has been around. And maybe even ecosystems that developed in complete isolation, separated from the rest of the planet by a wall of crushing, shifting, frozen weight. It's not just that we haven't fully explored it. It's that so far we simply can't. The Arctic doesn't just push back against entry. It wipes out our efforts. Machines fail. Sensors stop working. Ice seals over anything we try to send into its depths. The farther we go, the more the environment appears to resist. And yet, that's precisely why this mystery is so compelling. Because somewhere under all that ice is a world that's part Earth, part strange planet. And we're eager to discover what it's concealing. To grasp why it's so difficult to reach, we first need to understand what we're attempting to reach. Glaciers are not simply frozen water sitting still. They're active living systems, rivers of ice that shift and flow under their own massive weight. The glaciers around the North Pole are among the oldest and strongest on Earth. Some are over 2 million years old, built up and pressed together over countless freeze-thaw cycles. Picture snow falling year after year, century after century, never completely melting, pushing down on the layers below it until they merge into solid ice. Over thousands of years, that ice grows thicker, deeper, and starts to spread outward under its own enormous weight. That's what a glacier is: a slow, relentless river of ice grinding its way across the land, changing the earth under it. And these rivers aren't just thick, they're huge. The ice covering the Arctic Ocean and the Greenland ice sheet nearby can reach depths of more than 3 kilometers. That's like stacking 3 Eiffel Towers on top of each other and still not breaking through. It's not a frozen pond we're dealing with. It's a frozen continent, pushing down with unthinkable force. Now imagine what happens under that much ice. The weight is so powerful that it crushes the landscape below, cutting out deep valleys, subglacial basins, and hidden channels where meltwater can travel. In some spots, the pressure from above creates enough heat to melt the bottom layer of ice, even though the temperature stays well below freezing. That meltwater creates rivers and lakes beneath the glacier, locked away from the surface world. These are not the kinds of lakes you'd sail a boat across. They're pitch black, low in oxygen, and cut off from sunlight by kilometers of ice. And yet, some of them might have existed untouched for hundreds of thousands of years. Scientists understand this because we've explored similar places in Antarctica, like Lake Vostok, a huge body of water hidden beneath 4 kilometers of ice, untouched for maybe 15 million years. The Arctic almost certainly hides its own versions, but they stay invisible to us. Radar can suggest their presence. Satellite readings can pick up the smallest bulges and movements in the ice above. But to really study them, to see them, sample them, understand them, we'd need to get there. And that's where the challenges start. Drilling through kilometers of shifting ice isn't just difficult. It's one of the hardest engineering tasks humanity has ever tried. Ice isn't the same throughout. It's layered, filled with bubbles, cracked, and always moving. The deeper you drill, the more the pressure builds, and the more the ice acts like a thick fluid, flowing slowly around anything you try to push into it. Traditional drilling equipment, the kind used to reach oil or geothermal energy, isn't made for this. They depend on stable ground, not a constantly changing block of frozen water. Even specialized thermal drills, which melt their way down, face huge problems. As they go deeper, the ice can refreeze behind them, closing the shaft. The farther they go, the harder it is to keep a stable borehole. And even if you reach the bottom, there's another problem waiting: contamination. The ecosystems beneath the ice, if they're there, have been cut off for maybe hundreds of thousands or even millions of years. A single trace of modern bacteria brought in by a drill could destroy them before we ever learn about them. So scientists have to sterilize every part, every drop of fluid, every tool that enters the ice. That's slow, costly, and very delicate work. And under Arctic conditions, it gets even harder. The Arctic environment itself adds another layer of trouble. Unlike Antarctica, where most of the ice sits on top of land, the North Pole is covered by sea ice floating on an ocean. That ice isn't fixed. It moves, cracks, and shifts constantly because of winds and currents. A drilling platform that's perfectly placed one day might drift kilometers off target the next. Equipment anchored in the ice can be ripped apart by pressure ridges. massive walls of buckled ice that form without warning. Even the practical side of working in such a remote, harsh environment is challenging. Temperatures drop below -40 degrees Celsius. Winds can go over 100 kilometers per hour, and polar night can last for months, cutting off solar power and covering the region in total darkness. Every piece of equipment must be built to handle these extremes. Every mission must account for them, and every error can be disastrous. Some might wonder why we can't just send a submarine under the ice and explore from beneath. After all, nuclear submarines have traveled beneath the Arctic ice cap many times, and that's correct. But they haven't gone beneath the glaciers themselves. The reason is straightforward. Submarines are designed for open water, not for moving through the chaotic maze that exists under glacial shelves. Below a glacier, the space between ice and rock or ice and water is uneven and constantly changing. Caverns form and fall apart. Channels twist in unpredictable ways. Ice reaches downward in jagged ridges called keels, some dropping hundreds of meters below the surface. Even the most advanced submarines can't risk traveling through such terrain without detailed maps. And those maps don't exist because we haven't been able to go there. It's a perfect circle. We can't map the under-ice world because we can't get there. And we can't get there because we haven't mapped it. Robotic probes might look like an answer, and in some ways they are. Scientists are building autonomous underwater vehicles, AUVs, that can travel beneath ice, map the seafloor, and gather data. These robots can reach places humans can't, slip through tight passages, and work without direct control. But even they face serious limits. Communication through thick ice is almost impossible. Radio waves don't pass through it well, and sound signals break down quickly. That means once a robot goes beneath the ice, it's mostly on its own. If it gets stuck, broken, or lost, there's little we can do. Battery life is another big issue. Working in freezing temperatures uses up power quickly, and there's no way to recharge deep beneath the ice. Most current AUVs can only work for a few days or weeks before they have to surface. And surfacing isn't possible when you're trapped under a glacier. And then there's the pressure. The deeper under the ice you go, the greater the weight above you. At depths of several kilometers, the pressure reaches hundreds of atmospheres, enough to crush most materials if they're not built with extreme care. The ice itself creates extra mechanical stress. As it flows, it grinds against the rock below, creating friction and shear forces that can destroy equipment. Meltwater channels open and close without warning, sometimes flooding with sudden rushes, other times freezing solid. Even the most carefully built probe can find itself trapped or broken by forces we still don't completely understand. This is part of why exploration beneath the Arctic glaciers has moved so slowly. Every try teaches us more about what we don't know and how unprepared we are for the conditions that wait for us. It's easy to think of the Arctic as unchanging, a frozen, still wasteland. But that's one of the biggest misunderstandings about it. The glaciers are always moving, flowing outward from their centers toward the sea. That That movement can be measured in meters per year, but over decades or centuries, it reshapes the entire landscape beneath the ice. Caves fall apart, lakes shift, channels are swallowed, and new ones appear. Even the thickness of the ice changes as snow builds up, melts, refreezes, and compresses. For explorers, that means the target you're looking for may not even be there by the time you arrive. A subglacial lake spotted by radar today might have drained through a hidden channel by the time a drill gets there years later. A stable ice shelf might become filled with cracks and fractures after a season of warming. The Arctic is not a frozen grave. It's a living, moving system, and that makes it a constantly changing puzzle. Climate change is making that puzzle even trickier. The Arctic is warming almost 4 times faster than the global average. Sea ice is thinning and pulling back. Glaciers are melting at rates never seen before, and the delicate balance of pressure and temperature beneath the ice is changing. On one hand, that makes some areas easier to access. Thinner ice can be simpler to penetrate, and new channels might let waterborne probes explore farther. On the other hand, it makes conditions more unstable and dangerous. Ice shelves that once gave stable platforms for research now crack and collapse. Meltwater can refreeze in unexpected ways, sealing off routes and trapping equipment. And the very ecosystems we hope to study might be vanishing before we ever reach them, changed or destroyed by the rapid shifts above. Despite these barriers, scientists stay determined. The Arctic holds answers to some of the biggest questions in science about life, climate, and even other worlds. Subglacial environments could hold microbial life forms adapted to conditions we once thought impossible. Studying them could show how life survives in extreme places, giving clues to how it might exist on icy moons like Europa or Enceladus. The sediments beneath the ice hold records of past climates, locked away in undisturbed layers that go back hundreds of thousands of years. Opening those records could help us understand how Earth's climate has shifted and how it might shift again. And the physical processes beneath the glaciers could teach us about ice behavior, sea level rise, and the future of our polar regions in a warming world. But to reach those secrets, we must solve the problem that has stopped us for decades: how to safely, cleanly, and effectively get beneath the Arctic's frozen shield. There are ideas on the way. Some researchers are building cryobots, robotic probes designed to melt their way through ice using heat from nuclear power sources. These devices could, in theory, go down through kilometers of ice, carrying tools to study the water and sediment below. Others are trying laser drilling, using focused energy beams to cut narrow shafts through ice without the contamination risks of traditional methods. Still, others suggest hybrid systems that mix drilling with autonomous navigation, sending swarms of small probes that work together to map and watch the under-ice world. Each of these ideas faces huge technical and practical hurdles, but they show a growing drive to break through the barrier beneath the North Pole. Whether any of them will work remains to be seen. For now, the Arctic beneath the ice stays one of the last great mysteries on Earth. It's a place we know is there, but cannot yet reach. A hidden realm shaped by pressure, darkness, and time. Every attempt to explore it teaches us something new about our planet and about the limits of our technology and knowledge. But it also reminds us of something deeper. The Earth still keeps secrets from us. In an age where satellites map every mountain and drones scan every rainforest, the idea that an entire landscape, maybe an entire ecosystem, could stay hidden beneath our feet is both humbling and exciting. It's a reminder that exploration isn't just about going farther or faster. Sometimes it's about finding a way to go deeper into places that resist us, challenge us, and refuse to give up their mysteries easily. And as we move closer to that idea, we find that the story doesn't end with pressure or darkness or machinery that breaks because the ice itself is only part of the wall. Beneath it, there's something more. Something that makes us rethink how we explore, and even what it means to explore. That's where we go next, into the weight of a million winters, pressing down on a world we still can't reach, but can almost picture. Far above the lands where forests sway and rivers carve their winding paths, beyond the reach of roads, beyond even the lonely tundras that stretch to the horizon, there is a place where the Earth seems to hold its breath. Here at the top of the planet, water forgets how to flow, air forgets how to warm, and even sunlight loses its power. It is a realm ruled not by kings or nations, but by ice itself, an ancient shifting kingdom older than humanity's oldest stories. To really understand why we cannot yet explore beneath the North Pole's glaciers, we first need to understand the nature of this kingdom. Because it is not simply a place, it is a force. It shapes everything above it and hides everything below. And it does not give up its secrets easily. When you think about the North Pole, it's easy to picture it as a single point, a tiny dot at the top of a globe, a place you could plant a flag and call the top of the world. In reality, it is anything but simple. The geographic North Pole is not on land at all, but in the middle of the Arctic Ocean, a stretch of freezing water covered year-round by a shifting pattern of sea ice. Unlike the South Pole, where Antarctica's huge continental ice sheet sits firmly on rock, the Arctic's ice floats. It drifts with the currents, breaks apart, and reforms, melts, and refreezes in a pattern that has repeated itself for millions of years. The ice here is not still. It is alive, moving, breathing in a way that goes against our ideas about frozen landscapes. And this constant motion is one of the reasons it is so hard to break through and study what lies beneath. This frozen ocean is surrounded by land. The northern edges of North America, Europe, and Asia curve around it like a protective wall, closing in the Arctic basin. From Greenland to Siberia, from Alaska to Scandinavia, glaciers and ice caps spill into the sea, their frozen fingers reaching out into the drifting flows. Some of these glaciers are huge, stretching hundreds of kilometers across and reaching depths measured in kilometers. Others are smaller, but no less important, feeding the sea ice and shaping the Arctic environment in quiet but powerful ways. Together, they form a continuous frozen frontier that covers the top of the world, a kingdom of ice that is constantly shifting, collapsing, rebuilding, and growing. But calling it a kingdom isn't just poetry. In many ways, this frozen domain acts like a living thing with systems, cycles, and patterns all its own. The Arctic ice is not just water frozen in place. It's a dynamic structure, constantly reacting to changes in temperature, wind, ocean currents, and even planetary motion. In winter, the sea ice grows dramatically, covering nearly 14 million square kilometers, an area larger than the entire continent of Europe. In summer, it pulls back, shrinking to around 4 or 5 million square kilometers. But even at its smallest, this ice stays thick, often several meters deep, layered with snow and frozen meltwater that protect the sea below. Over time, sea ice can survive multiple seasons, becoming thicker, harder, and more impossible to break through. This multi-year ice, as scientists call it, is one of the greatest obstacles to any attempt to reach the waters and landscapes beneath. Beneath that surface layer, the complexity only grows. The Arctic Ocean is not a smooth bowl of water, but a rough seascape of ridges, basins, and underwater plateaus. At its deepest, it drops more than 5,400 meters into the Fram Basin, while the Lomonosov Ridge, an undersea mountain range, runs like a spine across the pole, splitting the ocean into two major basins. The mixing of ice and seafloor shape creates regions where ice is squeezed into towering ridges, areas where meltwater pools beneath the surface, and pockets where the ocean swirls and churns in slow, powerful gyres. Each of these features adds another layer of difficulty to the puzzle of under-ice exploration. It's not simply a matter of drilling straight down. Every meter is different from the one above it, shaped by forces we're only beginning to map. And then there is the sheer weight of it all. Ice might seem fragile when you hold a cube of it in your hand, but on the scale of glaciers and ice sheets, it is unbelievably heavy. Every square meter of glacier ice weighs about 900 kilograms per meter of thickness. Multiply that by hundreds or even thousands of meters, and the pressure becomes immense. The Greenland ice sheet, which takes up much of the Arctic's frozen landscape, contains enough ice to raise global sea levels by more than 7 meters if it were to melt completely. That's trillions of tons of frozen water pressing down on the rock below, carving valleys and basins, grinding mountains into silt, and sealing away whatever lies beneath under unthinkable weight. That pressure changes the very physics of water and rock. It melts ice at its base, even when the surface stays far below freezing. It reshapes bedrock and redirects groundwater. It creates sealed-off pockets where liquid water can exist in total darkness, cut off from the surface for thousands of years. It is in these sealed-off pockets that some of the Arctic's greatest mysteries lie. Scientists believe that beneath the Greenland ice sheet, and possibly beneath parts of the sea ice itself, there are vast networks of subglacial lakes and rivers. These hidden waterways are thought to carry melt water from the base of the ice sheet to the ocean, lubricating its flow and affecting how quickly it moves. Some may also hold microbial ecosystems that have evolved in total isolation, sustained by minerals from the bedrock and chemical energy sources rather than sunlight. These ecosystems, if they exist, could offer a look into how life might survive on icy moons elsewhere in the solar system, places like Europa or Enceladus, where oceans lie locked beneath kilometers of ice. But detecting these hidden lakes is hard enough. Reaching them is another challenge entirely. To even try such exploration, scientists rely on a collection of technologies that must work in some of the harshest conditions on Earth. Satellite radar altimetry can detect tiny changes in the height of the ice surface, hinting at liquid water far below. Airborne ice-penetrating radar can map the internal layers of glaciers, revealing hidden structures and possible water pockets. Seismic surveys can trace the echoes of sound waves through the ice and rock, offering hints about what lies beneath. But these tools can only go so far. They can tell us that something is there. They cannot show us what it is. For that, we would need to drill. And drilling through a moving, shifting, ever-changing mass of ice is a task so difficult that even the most advanced polar research teams approach it with caution. It's worth looking at what has been done in Antarctica to understand the scale of this challenge. At Lake Vostok, a subglacial lake buried beneath nearly 4 kilometers of ice, Russian scientists spent decades drilling carefully downward, using a combination of mechanical and thermal techniques to break through the ice without contaminating the water below. Even then, the project faced repeated problems. The drill shafts froze shut. Equipment broke down in the intense cold, and concerns about contamination delayed progress for years. The team finally reached the lake in 2012, but even that success raised more questions than it answered. Samples collected from the borehole were unclear, and the true nature of the ecosystem within remains largely unknown. If drilling through stable continental ice is that hard, imagine trying to do it in the Arctic, where the ice is thinner but less stable. The platform is floating, and the currents below are constantly shifting. Their layer of complexity comes from the political and practical realities of Arctic exploration. The region is bordered by 8 countries: Canada, Denmark via Greenland, Finland, Iceland, Norway, Russia, Sweden, and the United States, each with its own territorial claims, environmental rules, and strategic interests. Coordinating research in this geopolitical landscape is often as challenging as the science itself. Funding for large-scale polar projects is limited and highly competitive. Field seasons are short, often limited to a few months of relatively stable weather in the summer, and every expedition requires huge logistical support. Icebreakers to carve paths through the sea ice, aircraft to deliver supplies, and entire teams of engineers, scientists, and support staff willing to work in one of the harshest environments on Earth. Every kilogram of equipment must be flown or shipped thousands of kilometers. Every drop of fuel carefully rationed. Every mistake potentially fatal. the Arctic itself seems to work against us. The environment is unpredictable and harsh. Temperatures can drop below -50 degrees Celsius. Storms can show up without warning with winds strong enough to tear apart structures and scatter equipment. The sea ice itself can crack and shift beneath your feet, creating leads, sudden openings in the ice that can swallow machinery and people alike. In winter, darkness covers the region for months at a time, turning navigation into guesswork and making solar power useless. In summer, the sun never sets, melting the surface and creating slush that slows down vehicles and equipment. And beneath it all, the ocean continues its slow, powerful movement, pushing and pulling the ice in ways that can't always be predicted. It is a place of opposites, huge and fragile, ancient and constantly changing, unwelcoming, yet full of life. And perhaps the greatest opposite of all is this: for all its hostility, the Arctic is also one of the most important regions on Earth. Its ice reflects sunlight back into space, controlling global temperatures. Its waters drive ocean currents that shape weather patterns around the world. Its glaciers hold vast records of climate history, recording atmospheric changes in layers of snow and ice that stretch back hundreds of thousands of years. And its ecosystems, though sparse and hidden, are vital links in the planet's biological chain. The Arctic is not just a frozen wasteland at the edge of the map. It is a heartbeat of the Earth's climate system and a window into both our planet's past and its future. It's also worth noting that while the Arctic ice is ancient, it is not forever. Over geological timescales, the region has shifted dramatically. There were times millions of years ago when the Arctic was ice-free and covered with forests. There were other times when the ice extended far beyond its current limits, forming sheets that stretched deep into what are now mild regions. Even in the relatively short span of human history, the Arctic has gone through significant changes. During the last ice age, sea levels were more than 120 meters lower than they are today, and massive glaciers extended across much of the northern hemisphere. As the climate warmed, those glaciers pulled back, leaving behind the landscape we see now. Today, the Arctic is changing again, faster than at any point in recorded history. Sea ice is thinning, glaciers are retreating, and the delicate balance that has held for thousands of years is shifting. These changes make exploration both more urgent and more difficult. The window to study what lies beneath may be closing even as our ability to reach it slowly improves. To truly grasp the scale of this icy kingdom, it helps to think of it not as a single place, but as a layered world. At the top is the drifting sea, ice constantly moving, breaking, and reforming. Beneath that lies the freezing ocean, its waters separated into layers of different salinities and temperatures, shaped by currents that circle the Arctic basin in vast, slow-moving gyres. Below the water is the rugged seafloor carved by tectonic forces and covered in sediments that hold the history of past climates. And above the land surrounding this ocean sits the Greenland ice sheet and countless smaller glaciers pressing downward with their unthinkable weight. Together, these layers form a system that is at once connected and deeply isolated. Each influences the others, but each also hides its own secrets. It is within this maze of ice, water, and rock that the mysteries beneath the Arctic lie. And it is within this maze that our efforts to explore them so often fail. Standing at the surface, it's easy to forget that so much is hidden below. The Arctic appears empty, silent, barren. But beneath that silence lies a complexity that matches any rainforest or coral reef. Subglacial channels may carry melt water for hundreds of kilometers, connecting hidden lakes in networks we barely understand. Sediments beneath the ice may record the rise and fall of ice ages, preserving clues about how Earth's climate has changed and how it might change again. And if life exists in those sealed dark lakes, it could hold answers to some of the most profound questions in biology. How life begins, how it adapts, and where else in the universe it might exist. These are the treasures of the kingdom, locked in ice. But they remain beyond our reach, sealed away by forces we cannot yet overcome. This kingdom is not just distant. It is actively hostile to exploration. It moves when we need it to stay still. It freezes when we need it to melt. It crushes what we try to send into it and closes over the holes we dig. It hides its treasures not behind walls, but within itself, in layers of shifting, grinding, flowing ice that resist the tools and techniques we've built for other environments. And yet, for all its resistance, it continues to pull us closer, because beneath those shifting layers, there is something more than just water and rock and ancient ice. There are stories written in pressure and darkness, histories older than humanity, and perhaps even forms of life that have never seen the sun. As we look deeper into this frozen kingdom, we begin to realize that the problem isn't just about building better drills or stronger robots. It's about facing the fundamental physics of ice itself, the weight, the pressure, the movement, the constant reshaping of the world beneath our feet. And it's about understanding how those forces interact with the machinery we build and the ambitions we bring. Because beneath the surface of this icy realm lies a truth that has shaped it for millions of years. A truth that will shape everything we try to do there. And to see that truth clearly, we have to look not just at the surface or even the ice itself, but at the forces that hold it all together and make it so difficult to break through. If you were to stand on the ice near the top of the world and press your hand against its surface, you might think you were touching something delicate. Ice breaks under pressure. It melts when heated. It can be smashed with a hammer or carved with a blade. It feels fragile, temporary, something that should give way easily to human tools and machines. But beneath your feet, that thin sheet extends downward into a body of frozen water so vast, so heavy, and so relentless that it bends the land beneath it and changes the shape of the planet itself. The glaciers of the Arctic are not delicate. They are ancient, massive accumulations of snow and pressure built layer by layer over millions of winters. And their weight is one of the main reasons we cannot yet truly explore the world beneath them. every snowflake that has ever fallen on the polar ice adds to this immense weight. It starts with something almost laughably small. Tiny crystals drifting quietly down from the sky, piling on top of one another through storms and seasons year after year. Most melt away when summer sun returns, but those that don't become part of something larger. As they stack up, the snow at the bottom is pressed down by the layers above. Its delicate structure collapsing under the weight until it transforms into firn, a grainy material between snow and ice. Over centuries, as more snow builds up, that firn becomes dense glacial ice. What was once light enough to be carried by the wind becomes heavy enough to reshape continents. The Greenland ice sheet alone, the largest body of ice in the northern hemisphere, contains about 2.9 million cubic kilometers of frozen water. That's enough to cover the entire United States in ice more than 300 meters thick. Its weight is measured not in tons, but in trillions of tons. And that weight does not sit still. Ice flows. It does not flow quickly, at least not in human terms. But over decades and centuries, it acts less like a solid and more like an incredibly slow, thick liquid. Under the relentless pressure of its own mass, glacier ice bends and moves outward from its thickest points, creeping toward the sea in currents that carry rock and debris with them. This movement isn't even. It changes with temperature, bedrock friction, meltwater lubrication, and countless other factors. But no part of a glacier is truly still. Even the thickest ice, which might seem frozen in place, is creeping millimeters or centimeters each day. And the deeper you go beneath that ice, the more intense the pressure becomes, squeezing rock, water, and even the glacier itself into new shapes. For humans and machines trying to break through this frozen world, that movement is an enemy we have yet to beat. It bends drilling shafts, closes tunnels, and crushes anything that stays too long. To grasp just how overwhelming this pressure is, consider the numbers. For every 10 meters of ice above a point, there's roughly 1 atmosphere of pressure, about 14.7 pounds per square inch. That means that beneath 1,000 meters of ice, the pressure goes beyond 100 atmospheres. At 3,000 meters, as at the base of parts of the Greenland ice sheet, the pressure surpasses 300 atmospheres, more than 4,400 pounds per square inch. Few materials on Earth can handle such force forever without bending. Steel can bend, glass can shatter, even rock will give and flow over geological time. At those pressures, water acts differently too. Its melting point drops, allowing it to stay liquid even when temperatures are below freezing. That means at the base of a glacier, where pressure is highest, liquid water often exists in thin layers or pockets, lubricating the ice above and helping it slide over the bedrock. This melt water is vital to the glacier's movement, but it also creates unpredictable conditions for explorers. A drill can suddenly hit liquid water after kilometers of solid ice, destabilizing the borehole and threatening contamination of pristine subglacial environments. The pressure doesn't just act downward. As the glacier flows outward, it puts out immense sideways forces as well, grinding against the valley walls and the bedrock below. The base of a glacier is not smooth. It's a chaotic zone of rock pieces, sediments, and meltwater, all being dragged along under crushing weight. This process, called glacial erosion, has carved out some of the world's most dramatic landscapes. U-shaped valleys, fjords, and basins that were once buried beneath miles of ice. But it also means that the space between ice and bedrock is constantly changing. Cavities open and close. Water channels shift. Sediment builds up and is swept away. For any machine trying to work in this environment, predictability is nearly impossible. A probe lowered into one channel might find it sealed off by refreezing water days later. A drilling shaft might emerge into a cavity that didn't exist when the project started. The glacier is always reshaping itself, always rewriting the landscape below. This constant pressure also changes the shape of the land itself. The Earth's crust, though seemingly solid, is elastic on long time scales. When a massive glacier forms, its weight pushes the crust downward, pressing the land beneath it. This phenomenon, known as isostatic depression, can lower the surface by hundreds of meters. When the glacier melts, the crust slowly bounces back, a process called isostatic rebound, but it can take thousands of years. In places like Canada and Scandinavia, the land is still rising today as it recovers from the weight of ice sheets that melted at the end of the last ice age more than 10,000 years ago. Under the Arctic glaciers, this back and forth between ice and rock is ongoing. As the ice thickens and thins, advances and retreats, it bends the crust below, changing groundwater flow, creating new channels, and reshaping the very foundations of the landscape. That means the world beneath the ice isn't just hidden. It's alive, dynamic, and constantly changing under forces far beyond our control. It's not only the land that feels this pressure. The ocean beneath the Arctic sea ice is also affected. Sea ice might seem thin compared to the Greenland ice sheet, but it still puts significant weight over vast areas. That weight pushes down on the water below, changing currents and mixing patterns. Combined with the pressure from the glaciers that spill into the sea, it shapes the circulation of the Arctic Ocean itself. This circulation, in turn, affects the distribution of nutrients, the formation of deep water masses, and even global climate patterns. The Arctic is a crucial engine in Earth's climate system, and the weight of its ice is one of the pistons driving that engine. Any attempt to explore beneath it must deal not only with the pressure of the ice itself, but with the ocean it helps shape, a dynamic, powerful body of water that is as much a part of the system as the ice above it. For the machines we design, this pressure is more than a problem. It is a fundamental wall. Traditional drilling equipment is built for rock, not ice. It's designed to bore through relatively stable materials under predictable conditions. In ice, everything is different. The material flows. It melts and refreezes. It puts out pressure in unpredictable ways. Drill shafts can buckle under the stress. Boreholes can close as the ice flows around them. Melt water can refreeze above the drill bit, trapping it deep within the glacier. And even if the equipment survives the journey downward, the conditions at the base, crushing pressure, unpredictable water pockets, unstable sediments, can make it useless. Building machines that can work reliably in these conditions requires not just stronger materials, but entirely new approaches to engineering. Even the most advanced robotic probes face similar challenges. Autonomous underwater vehicles designed to explore beneath ice must handle immense pressure while moving through complex shifting environments. Their hulls must be strong enough to resist crushing forces, yet light enough to allow for movement. Their sensors must work in conditions of near total darkness and intense cold. Their power systems must run reliably even as temperatures drop and pressures climb. And perhaps most challenging of all, they must do all of this without direct communication. Radio waves can't get through thick ice, and sound signals break down quickly, leaving the robots largely on their own once they enter the under-ice environment. A failure deep beneath a glacier doesn't just mean the loss of expensive equipment. It means the loss of data, of progress, of years of preparation and planning. The pressure also creates a risk to what we're trying to study. If subglacial lakes and ecosystems exist beneath the Arctic ice, they have evolved in conditions that are almost entirely sealed off from the surface. Bringing in even a small amount of contamination could permanently alter those environments. But sterilizing equipment for use under such pressure is extremely difficult. Materials that are sterile at the surface may be compromised under hundreds of atmospheres of force. Fluids used in drilling can act unpredictably, expanding or shrinking in ways that create pathways for contamination. Even the act of drilling itself, the heat created, the vibrations produced, can disturb delicate environments. Balancing the need to explore with the need to protect these pristine systems is one of the greatest ethical and scientific challenges we face. It's easy to underestimate just how much time is embedded in that pressure. Each layer of ice represents a winter, a season of snow that fell and never melted, pressed into the fabric of the glacier. In some places, the ice at the base of Greenland's sheet is more than 1 million years old. That means the water trapped beneath it has been sealed away since before modern humans existed. The pressure we encounter there is not just physical, it's about time. It's the weight of countless winters pressing down season after season, century after century, until the past itself becomes a barrier. Every attempt to break through that barrier is an attempt to move through time, to reach back into Earth's distant history and touch something that has remained unchanged for longer than our entire species has walked this planet. And beneath that weight, in the darkness where pressure turns ice into something almost alive, there may be life itself, the kind we're used to seeing, forests or oceans teeming with visible creatures, but microbial life. Bacteria, archaea, perhaps even organisms we don't yet have names for, all existing in conditions that seem impossible. No sunlight, no oxygen from the atmosphere, temperatures hovering near freezing, pressures that would crush most living things instantly. And yet, life might persist. We know this because we found it before in other extreme environments. Deep in the ocean where no light reaches, in boiling hot springs, in acid lakes, in rocks miles beneath the surface. Life, it turns out, is more resilient and adaptable than we ever imagined. The subglacial lakes of Antarctica have already hinted at this possibility. When Russian scientists finally reached Lake Vostok after decades of drilling, they found signs of microbial life in the water samples they collected. The results were controversial and hard to interpret because of contamination concerns, but they suggested that even in one of the most isolated environments on Earth, life had found a way. If Lake Vostok can harbor life, then the hidden lakes beneath the Arctic ice almost certainly can too. And studying them could answer questions that go far beyond Earth. Astrobiologists, scientists who study the possibility of life beyond our planet, are particularly interested in these subglacial ecosystems. Why? Because they're the closest analog we have to the conditions on icy moons in our solar system. Europa, a moon of Jupiter, is covered in a thick shell of ice beneath which lies a vast ocean. Enceladus, a moon of Saturn, has geysers that shoot water vapor into space, hinting at liquid water beneath its frozen surface. If life can exist in the dark, pressurized lakes beneath Earth's glaciers, sustained by chemical energy rather than sunlight, then it might also exist in the oceans of Europa or Enceladus. Studying Arctic subglacial life could teach us not just about Earth, but about the potential for life throughout the universe. But to study that life, we first have to reach it. And that brings us back to the fundamental problem, the weight pressing down from above. Every solution we've tried so far has been partial at best. Mechanical drills can bore through ice, but they're slow, prone to getting stuck, and risk contamination. Thermal drills can melt through more quickly, but they use enormous amounts of energy and can create unstable boreholes. Robotic probes can explore once they reach the water, but getting them there in the first place remains a massive challenge, and every approach must contend with the same enemy: the relentless, crushing pressure of millions of tons of ice. Some researchers have proposed radical solutions. One idea is to use nuclear-powered cryobots, torpedo-shaped probes that melt their way through ice using heat from a small nuclear reactor. These devices could theoretically descend through kilometers of ice without human intervention, carrying instruments to analyze the water and sediments they encounter. The technology is still experimental, but it's being developed with missions to Europa in mind. If we can build a cryobot that works beneath Earth's glaciers, we might be able to send one to an alien moon. Another approach involves using lasers to cut through ice. High-powered laser beams can vaporize ice without physical contact, potentially creating cleaner boreholes with less risk of contamination. But lasers require enormous amounts of power, and focusing them through kilometers of ice presents its own challenges. The ice itself can scatter and absorb the beam, reducing its effectiveness the deeper it goes. Still, researchers continue to experiment, refining the technology and searching for ways to make it practical for real-world exploration. A third idea involves using networks of small, cooperating robots rather than a single large probe. Imagine dozens or even hundreds of tiny autonomous devices, each carrying sensors and communication equipment, working together to map and explore the under-ice environment. If one fails, the others continue. If one finds something interesting, others can converge on that location. This swarm approach is inspired by nature, by the way ants and bees work together to accomplish tasks no individual could manage alone. It's an elegant solution in theory, but building robots small enough to deploy in large numbers, yet tough enough to survive Arctic conditions, is a significant engineering challenge. Each of these approaches represents a different way of thinking about the problem, but all of them must ultimately confront the same reality. The ice is heavy, it's moving, and it doesn't want to let us in. The weight of 1,000,000 winters presses down with a force that transforms physics itself, turning solid water into a flowing, crushing barrier that has kept its secrets for longer than humanity has existed. And as we stand at the surface, looking down into that frozen darkness, we begin to understand that this isn't just a technical challenge. It's a confrontation with time, with pressure, with the raw power of a planet that shapes itself according to laws far older than us. But the weight is only part of the story. Because even if we could somehow drill through the ice, even if we could send probes into the darkness below, we would still face another challenge that might be even harder to overcome. Darkness itself. Not just the absence of light, but the kind of darkness that transforms everything it touches. The kind that has existed unbroken for hundreds of thousands of years, sealing away entire ecosystems in a blackness so complete that the very concept of sight becomes meaningless. When we think about exploration, we usually imagine going to places we can see, mountains we can climb, oceans we can sail across. Even when we explore the deep sea, we bring lights with us, pushing back the darkness to reveal what's hidden. But beneath the Arctic glaciers, light is not just absent, it's forbidden. The ice above is so thick, so dense, that not a single photon of sunlight has reached the water below in more time than we can easily comprehend. This is not the darkness of a moonless night or a deep cave. This is absolute darkness, the kind that existed before stars, the kind that fills the spaces between galaxies. And in that darkness, everything changes. Without light, there can be no photosynthesis. Without photosynthesis, there can be no plants, no algae, none of the organisms that form the base of most food chains on Earth. Any ecosystem that exists beneath the ice must be built on something else entirely. It must draw energy not from the sun, but from the earth itself, from chemical reactions in the rock, from geothermal heat seeping up from below, from the breakdown of minerals and the slow decay of ancient organic matter trapped when the ice first formed. These are called chemosynthetic ecosystems, and they represent a completely different way of life, one that doesn't depend on the sun at all. We've found chemosynthetic ecosystems in other extreme environments, around hydrothermal vents on the ocean floor, where superheated water rich in minerals pours out from cracks in the Earth's crust. In deep caves where bacteria feed on sulfur compounds in the rock, even in the human gut, where microbes break down food and extract energy without ever seeing sunlight. These discoveries have revolutionized our understanding of what life needs to survive. It turns out that life doesn't need the sun. It just needs energy in some form and liquid water. And beneath the Arctic ice, both of those things might exist. But studying life in absolute darkness presents unique challenges. For one thing, we can't see it, at least not without bringing our own light sources. And even then, we have to be careful. Organisms that have evolved in total darkness for millions of years might be sensitive to light in ways we can't predict. A flash of light from a probe's camera could damage or kill them before we even understand what they are. It's like shining a spotlight directly into eyes that have never known anything but darkness. The shock alone could be devastating. Even if we can bring light safely, finding life in these environments is difficult. Subglacial ecosystems, if they exist, are likely sparse. We're not talking about dense forests or coral reefs. We're talking about microbes, possibly just a few cells per milliliter of water, scattered through vast, dark lakes. Finding them requires sensitive instruments that can detect tiny chemical signatures or genetic material in samples that might contain almost nothing. It requires patience, careful analysis, and the ability to tell the difference between life and contamination from our own equipment. The darkness also affects how we navigate and map these environments. In the ocean, we use sonar and other acoustic tools to build pictures of what's around us. Sound waves bounce off objects and return, allowing us to create maps even when we can't see. But beneath glaciers, the environment is cluttered with ice, rock, and sediment. Sound waves bounce and scatter in unpredictable ways, creating echoes and false readings. A probe might think it's found an open channel when it's actually heading toward a wall. might miss a large cavity entirely because the acoustic signature gets lost in the noise. And then there's the psychological weight of that darkness. Not for the machines we send down, obviously, but for the scientists who design the missions and analyze the data. There's something deeply unsettling about exploring a place where nothing has ever been seen, where no light has ever reached. It's one thing to explore the deep ocean, knowing that the sun shines on the surface above. It's another to explore beneath kilometers of ice, knowing that the darkness is sealed in on all sides. That isolation, that complete separation from the world we know, adds a layer of difficulty that's hard to quantify, but impossible to ignore. Still, darkness can also be an advantage in some ways. In the absence of light-dependent life, the ecosystems beneath the ice might be simpler, more manageable to study. Without the complexity of photosynthesis and all the organisms that depend on it, we might be looking at a more basic form of life, closer to what existed on early Earth before oxygen filled the atmosphere and the sun became the dominant energy source. Studying these simple ecosystems could teach us about the origins of life itself, about how the first living things emerged and survived in a world very different from the one we know today. The darkness also means that these environments are incredibly stable. Without sunlight, there are no daily or seasonal cycles, no summers or winters, no day or night. The temperature stays constant, hovering just above or below freezing, depending on pressure and geothermal heat. The chemistry stays constant, changing only slowly as minerals dissolve from the rock and gases seep in from below. This stability means that any life that exists there has had millions of years to adapt to very specific conditions. It might be highly specialized, perfectly tuned to its environment in ways that make it unlike anything we've ever seen before. But that specialization also makes it vulnerable. If we disturb these environments, if we introduce heat, light, or foreign chemicals, we might destroy them before we ever understand them. That's why contamination is such a serious concern. It's not just about preventing Earth microbes from colonizing alien environments like Europa. It's about protecting the alien environments right here on our own planet, the ones that have been sealed away in darkness for so long that they might as well be on another world. Beyond the biological darkness, there's a different kind of darkness we face, the darkness of ignorance. We simply don't know what's down there. We have theories, models, educated guesses based on what we've learned in Antarctica and other extreme environments. But the Arctic beneath the ice remains largely unexplored. We don't know how many subglacial lakes exist. We don't know how big they are or how they're connected. We don't know what minerals are dissolved in the water or what gases are present. We don't know if there's life, and if there is, we don't know what form it takes or how it survives. This darkness of knowledge makes planning any exploration incredibly difficult. When you explore a place you know nothing about, every decision is a guess. Where do you drill? How deep do you go? What instruments do you bring? What samples do you collect? Each choice is made in the dark, both literally and figuratively, with no guarantee that it's the right one. And because each mission is so expensive and difficult, each mistake costs years of time and millions of dollars. There's no room for trial and error, no opportunity to quickly adjust and try again. Every attempt must be as close to perfect as possible, even though perfection is almost impossible when you're working blind. The darkness beneath the ice also extends to time. These environments have been isolated for so long that they represent a kind of time capsule, a window into Earth's distant past. The water in some of these lakes hasn't been in contact with the atmosphere for hundreds of thousands of years. It might contain dissolved gases from ancient air, chemical signatures from past climates, even traces of life forms that went extinct on the surface long ago. Studying these time capsules could help us understand how Earth's climate has changed over geological timescales, how ice ages come and go, how the planet responds to shifts in temperature and atmospheric composition. But accessing that information requires more than just reaching the water. It requires collecting samples without contaminating them, storing them properly, and analyzing them with techniques sensitive enough to detect signals from the distant past. It requires separating the ancient from the modern, the pristine from the polluted, and it requires doing all of this in one of the harshest environments on Earth, where equipment fails, temperatures plunge, and every operation is complicated by the sheer difficulty of being there. There's also a philosophical darkness we must confront. The question of whether we should be there at all. If these environments have remained undisturbed for millions of years, do we have the right to disturb them now? If life exists in these dark lakes, sealed away from the rest of the planet, do we have the right to expose it to our presence, our tools, our contamination? These are not easy questions, and they don't have simple answers. Some argue that the scientific value of exploration outweighs the risks, that understanding these environments could help us protect the planet and search for life elsewhere in the universe. Others argue that some places should remain untouched, that there are limits to where human curiosity should reach. In many ways, the darkness beneath the ice forces us to confront these questions more directly than exploration of other environments. When we explore the ocean or climb mountains, we're entering places that are already part of our world, already connected to the systems we know and interact with. But the subglacial world is different. It's been separated, sealed away, kept apart from the rest of Earth for longer than our species has existed. Breaking that seal, penetrating that darkness, is an act that can't be undone. Once we're there, once we've introduced our presence, the isolation ends. The darkness is broken, and whatever was there before is changed forever. This weight of responsibility is something that researchers take seriously. International agreements and protocols govern polar exploration, requiring strict sterilization procedures and careful planning to minimize contamination. But even with the best intentions and the most careful precautions, there's always risk. A single microbe hitching a ride on a drill bit, a trace of hydraulic fluid leaking into the water, a change in temperature or pressure caused by the drilling process itself. Any of these could alter or destroy what we're trying to study. And yet, despite all these challenges, despite the physical darkness, the darkness of ignorance, and the moral darkness of uncertainty, scientists remain drawn to these hidden places because the potential discoveries are too important to ignore. If we find life beneath the ice, it would transform our understanding of biology, showing us that life can exist in conditions we once thought impossible. If we find evidence of past climates, it would help us predict future changes and understand the long-term dynamics of our planet. If we find nothing, that would be valuable too, helping us understand the limits of where life can exist and where it cannot. The darkness beneath the ice is not just a problem to be solved. It's a fundamental part of what makes these environments so mysterious and so compelling. It's a reminder that even on Earth, even on a planet we've mapped and studied for centuries, there are still places that remain beyond our reach. Places where the darkness is so complete, the isolation so total, that they might as well be on another world. And in reaching for them, in trying to push back that darkness and bring light to places that have known only blackness for millions of years, we're not just exploring our planet. We're testing the limits of what it means to be human, to be curious, to reach for knowledge even when the cost is high and the answers are uncertain. As we drift deeper into this thought, into this understanding of what lies beneath, we begin to see that the barriers we face are not just physical. They're not just about drilling through ice or building robots that can survive pressure. They're about confronting darkness in all its forms. The darkness of the unknown, the darkness of isolation, the darkness of responsibility, and perhaps most profoundly, the darkness of time itself, pressing down on these sealed worlds with the weight of ages, keeping them hidden not behind walls of ice alone, but behind walls of history, of evolution, of secrets that have remained unspoken since before humanity even existed. And so we arrive at a place in this story where the physical and the philosophical begin to merge, where the ice, the pressure, the darkness, and the sheer passage of time combine into something larger than any single obstacle. They form a barrier not just of matter, but of meaning. A boundary that asks us to consider what exploration truly costs and what it truly means. The Arctic beneath the ice is not simply inaccessible because our drills aren't strong enough or our robots aren't advanced enough. It's inaccessible because it exists at the intersection of extremes. Extreme cold, extreme pressure, extreme isolation, extreme age. Each of these factors alone would present serious challenges. Together, they create an environment so hostile, so removed from human experience, that even our most sophisticated technology struggles to function there. Consider the cold. At the surface, Arctic temperatures can drop to -50 degrees Celsius or lower. But beneath the ice, temperatures hover near the freezing point of water under pressure, typically between -2 and 0 degrees Celsius. That might not sound as extreme, but it creates its own problems. At these temperatures, materials behave differently. Metals become brittle. Plastics lose flexibility. Lubricants thicken or freeze entirely. Electronics can fail as semiconductors change their properties. Batteries drain rapidly as chemical reactions slow down. Every component of every machine must be specially designed and tested to operate reliably in these conditions. And even then, failures are common. The cold also affects the ice itself in ways that complicate exploration. Ice near the freezing point is more plastic, more prone to deformation and flow. That means it can close around drilling equipment more quickly, sealing off boreholes and trapping tools. It can also create zones of weakness where the ice fractures unpredictably, opening crevasses that can swallow equipment or researchers. And because the temperature varies with depth and location, conditions can change dramatically over short distances. A probe might encounter solid, stable ice one moment and flowing, unstable ice the next, with no warning. Then there's the question of time, not geological time, but operational time. Every mission to the Arctic has a limited window. Brief summer months when temperatures are marginally warmer and travel is slightly less dangerous. But even in summer, conditions are harsh and the window is short. Equipment must be transported, often over vast distances. It must be assembled in the field under difficult conditions. Drilling must begin, proceed, and hopefully succeed before winter returns and the opportunity is lost. If something goes wrong, if equipment fails or weather delays operations, there might not be time to fix it. The mission simply ends, and everything must wait another year. This time pressure adds stress to every decision. Should we proceed even though conditions aren't ideal? Should we take a risk with uncertain equipment because this might be our only chance? Should we push forward even when data suggests we should stop? These are the kinds of questions that field teams face constantly, and there are no easy answers. The cost of being too cautious is failure to achieve the mission's goals. The cost of being too aggressive is potentially catastrophic equipment failure or environmental contamination. Walking that line requires experience, judgment, and sometimes a bit of luck. But perhaps the deepest challenge we face is one of perspective. We're trying to explore an environment that operates on time scales and spatial scales that are almost impossible for human minds to fully grasp. When we look at a glacier, we see something that appears static, unchanging, but it's actually flowing, moving, reshaping itself over decades and centuries. The channels and cavities beneath it that we might want to explore today might not exist in the same form in a year or 10 years. The lakes we detect with radar might drain or refill over time scales we're only beginning to understand. This mismatch between human time and geological time makes planning difficult. We design missions based on data that's often years old by the time the mission launches. We drill toward targets that might have moved or changed. We try to study processes that unfold over centuries by observing them for days or weeks. It's like trying to understand a movie by looking at a single frame, or trying to grasp the plot of a novel by reading a single word. The picture we get is incomplete, fragmented, and potentially misleading. And yet, this is the nature of scientific exploration at the frontiers of knowledge. We work with what we have. We make the best observations we can. We build models and test hypotheses. We refine our understanding one small piece at a time. The process is slow, frustrating, and often inconclusive. But it's also the only way forward. Each mission, successful or not, adds to our knowledge. Each attempt teaches us something about the environment, the technology, or ourselves. There's something almost poetic about this struggle. Humanity, with all our intelligence and technology, confronted by a simple thing, frozen water. But it's not simple at all, is it? Ice, when accumulated over millions of years, when subjected to immense pressure, when sealed away from light and warmth, becomes something extraordinary. It becomes a force of nature as powerful as any volcano or earthquake. It shapes continents, drives ocean currents, stores vast amounts of Earth's history in its frozen layers, and it guards its secrets jealously, yielding them only to those willing to face its full power. In many ways, the Arctic beneath the ice represents the last truly unexplored frontier on Earth. We've climbed the highest mountains. We've descended to the deepest ocean trenches. We've sent robots to Mars and probes to the edge of the solar system. But we still can't reliably reach beneath our own planet's ice sheets. We still can't answer basic questions about what's there, what lives there, what secrets are locked away in those dark, pressurized lakes. This fact is both humbling and inspiring. Humbling because it reminds us of our limitations, of how much we still don't know about our own world. Inspiring because it gives us something to strive for, a genuine mystery to solve, a frontier that still challenges us. The scientists and engineers working on these problems are driven by more than just curiosity, though curiosity is certainly part of it. They're driven by the knowledge that understanding these environments could have profound implications for humanity. The ice sheets of Greenland and Antarctica contain enough frozen water to raise global sea levels by more than 60 meters if they were to melt completely. Understanding how they behave, how they respond to warming, how quickly they might collapse or stabilize, is critical to predicting and preparing for future climate change. Billions of people live in coastal areas that could be affected by rising seas. The fate of those communities may depend, at least in part, on what we learn from exploring beneath the ice. There's also the question of life beyond Earth. If we can't figure out how to explore beneath our own planet's ice, how will we ever explore beneath the ice of Europa or Enceladus? Those missions, if they happen, will face all the same challenges we face in the Arctic, plus the added difficulties of operating millions of kilometers from Earth with no possibility of repair or rescue. Every lesson we learn in the Arctic, every technique we develop, every mistake we make and learn from, brings us one step closer to being able to explore those distant frozen worlds. In that sense, the Arctic is not just a scientific frontier. It's a training ground for future exploration beyond Earth. But even beyond the practical implications, there's something deeply human about the desire to know what's beneath the ice, to reach the unreachable, to see the unseen, to bring light, literally and figuratively, to places that have known only darkness. This drive to explore, to push boundaries, to solve mysteries, is part of what makes us human. It's what led our ancestors to cross oceans, climb mountains, and eventually leave the planet entirely. The Arctic beneath the ice is simply the latest chapter in that ongoing story. As we stand at the edge of this frozen frontier, looking down at the ice beneath our feet, we're confronted with a simple truth. The Earth still has secrets. Despite all our satellites, all our sensors, all our accumulated knowledge, there are still places on this planet that remain mysterious. Still places that defy our attempts to understand them. Still places that remind us how much we have yet to learn. And perhaps that's exactly as it should be. Perhaps we need these mysteries. Perhaps we need places that resist us, that challenge us, that force us to push the boundaries of our technology and our understanding. Because in pushing those boundaries, we don't just learn about the world, we learn about ourselves. We discover what we're capable of when faced with seemingly impossible challenges. we find new ways to solve problems, new technologies, new approaches that often have applications far beyond the original challenge. The Arctic beneath the ice is teaching us patience. It's teaching us humility. It's teaching us that some things can't be rushed, can't be solved by simply throwing more money or more technology at the problem. It's teaching us to think carefully, to plan thoroughly, to respect the environments we study, and to understand the consequences of our actions. These are lessons that extend far beyond polar exploration. They're lessons about how we interact with our planet, how we pursue knowledge, and how we balance our desire to know with our responsibility to protect. In the end, the question of whether we'll ever truly explore beneath the Arctic ice is not just a technical question. It's a question of will, of persistence, of creativity, and of wisdom. We have the intelligence to develop the necessary technology. We have the resources, if we choose to allocate them. We have the motivation, with climate change making these studies more urgent every year. What we need now is patience, careful planning, and the wisdom to proceed in ways that protect these fragile environments even as we study them. The ice above is still there, thick and unyielding. The pressure is still immense. The darkness is still absolute. The secrets are still sealed away. But slowly, incrementally, we're learning. We're developing better tools, better techniques, better understanding. Each year brings us a little closer. Each mission, even those that fail, teaches us something valuable. And someday, perhaps not in the immediate future, but someday, we will break through. We will reach those hidden lakes. We will sample their waters, study their chemistry, search for signs of life. We will bring light to the darkness and knowledge to the unknown. And when that day comes, when we finally pierce the veil beneath the North Pole and discover what has been hidden there for millions of years, it will be because we refused to give up. Because we faced every obstacle, the weight, the pressure, the cold, the darkness, the sheer difficulty of it all, and kept pushing forward. Not recklessly, but thoughtfully. Not carelessly, but with respect for what we might find. And in that moment of discovery, whenever it comes, we'll understand something profound, not just about the Arctic, not just about ice or climate or life in extreme environments, but about what it means to be human, to be curious, to explore, to reach for knowledge even when the path is difficult and the destination uncertain. For now, though, the ice remains, silent, heavy, guarding its mysteries as it has for countless ages. And we remain at the surface, looking down, planning, preparing, dreaming of the day when we'll finally know what lies beneath. The kingdom of ice stands firm, but kingdoms, even frozen ones, cannot hold their secrets forever. Not when humanity is determined to discover them. And with that thought, with that understanding of where we are and where we're trying to go, we come to the end of tonight's journey. The North Pole's glaciers still loom above their hidden world. still pressed down with the weight of a million winters, still seal away mysteries that have remained untouched since before our species existed. But now you know why. You understand the forces at work, the challenges we face, the questions we're trying to answer. Thank you for joining me on this quiet exploration tonight. If you found this journey meaningful, I'd be grateful if you'd subscribe to Mr. Sleepy Science or share this video with someone who might appreciate a moment of peaceful curiosity. Until next time, rest well, dream deeply, and remember that even in our mapped and measured world, there are still places that hold their secrets close, still frontiers waiting to be explored, still mysteries calling to us from the darkness beneath the ice. Good night.